Well, enough people had asked me about exactly what I was looking for in a precipitation reaction video that I decided to make a demo of my own. And so this screencast is going to be on the precipitation of aluminum hydroxide. And aluminum hydroxide is actually something that I didn't assign to anybody. And by the time this video is over, you will understand why. But what is aluminum hydroxide? Aluminum hydroxide has the formula AlOH3. It's a naturally occurring mineral. It's known as gibbsite, and it is obtained from an ore called bauxite. And bauxite is the main source of aluminum in mining for aluminum ores. Okay. So now in this video, we're going to talk about making gibbsite or aluminum hydroxide from a precipitation reaction. But actually, most aluminum hydroxide in the world is obtained from is gibbsite that is obtained from bauxite ore, and it's an important part in the commercial preparation of aluminum metal. And so you start with bauxite ore, which is kind of a funky looking thing. This kind of looks like a paving stone, but it's full of aluminum minerals, among which is gibbsite. So you can extract from the bauxite gibbsite, which is aluminum hydroxide, which is again the subject of our video today. You can take gibbsite and you can dehydrate it to form alumina, which is aluminum oxide, and then that is by reduced by a process of electrolysis into aluminum, among other things, aluminum foil. All right, well, we're going to make it by a precipitation reaction, so let's observe a couple examples. So here's a young fellow. If you watch, he's going to mix a couple ingredients together, and you'll see a precipitate forming in this beaker here. That is aluminum hydroxide. There's a different video with another guy. He's going to mix a couple of compounds together, and you'll see that precipitate. I want you also to notice that there's gas bubbling out of this as well when he's making the aluminum hydroxide. What you've seen there are a couple of examples of a precipitation reaction, and a precipitation reaction in general is a reaction in which you have water-soluble reactants that when you mix them together give you an insoluble product. And this is a type of double displacement reaction, and it occurs with ionic compounds. So you mix two water-soluble ionic compounds and you get two products, one of which is water-soluble, but the other one is not, so it precipitates out of solution. So here we are making aluminum hydroxide. And one of the substances that they were mixing together to make aluminum hydroxide was aluminum sulfate. So of course, you can infer from that that the other reactant must be something like sodium hydroxide, right? So that you have aluminum ions and hydroxide ions to give you aluminum hydroxide. Well, remarkably, it is not a hydroxide compound, the second compound they were mixing together there. It was aluminum sulfate, but it was what they were adding to it was sodium bicarbonate, which is better known to you perhaps as baking soda. And so I'd imagine that raises a giant question mark, like how is that possible that you mix aluminum sulfate and sodium bicarbonate and get aluminum hydroxide? Because there aren't any hydroxide ions here. Well, here's the reason why I didn't assign this to anybody, because there's more going on here than in a typical precipitation reaction. Turns out that when you take sodium hydroxide and dissolve it in water, you get a little reaction that occurs in which sodium bicarbonate and water react to give sodium hydroxide plus carbonic acid. Now, this reaction doesn't go very far on its own, but you can use a thermodynamic principle known as Le Chatelier's principle to drive it forward by using the products of that reaction to do something else. So in this case, the sodium hydroxide that's generated is now reacting with aluminum ions to make aluminum hydroxide, and the carbonic acid, which is what this other thing is called, decomposes to form water plus carbon dioxide, which is the bubbles that you saw. So now we can put all these reactions together, and I've multiplied them so that they're balanced. Turns out you need 6 sodium bicarbonates to make 6 sodium hydroxides. Those 6 sodium hydroxides then react with aluminum sulfate to give you 2 aluminum hydroxides plus 3 sodium sulfates, and your 6 carbonic acids decompose into 6 waters plus 6 carbon dioxide. Well, that's a lot to add together, but as it turns out, just as with spectator ions, we can look for things that appear on both sides of the arrow here and get rid of them. And that includes water, sodium hydroxide, and carbonic acid. And so now when I combine everything together without those pieces, I get this equation. Aluminum sulfate plus sodium bicarbonate gives me aluminum hydroxide plus sodium sulfate plus carbon dioxide. Well, now I can write that as an ionic equation. Aluminum sulfate gives me 2 aluminums plus 3 sulfates. 6 sodium bicarbonates gives me 6 sodiums plus 6 bicarbonates. I get 2 aluminum hydroxides. 3 sodium sulfates give me 6 sodiums plus 3 sulfates. And I have my 6 carbon dioxides. I can identify sodium as a spectator ion. I can identify sulfate as a spectator ion. And I can write the net ionic equation, which is 2 aluminum ions plus 6 bicarbonate ions give me 2 aluminum hydroxides plus 6 CO2. So again, there's a lot going on here. It's more than your typical precipitation reaction. This actually involved a precipitation reaction, an acid-base reaction, a decomposition reaction, and the thermodynamics of Le Chatelier's principle. I hope you enjoyed the show.